Okay, well, it's 1 o'clock, so let's get started with our next speaker. Our next speaker will be Ashani Dasgupta from University of Wisconsin-Milwaukee, speaking about local connectedness of Bowditch boundaries of relatively hyperbolic groups, as you can all read. So take it away, Ashani.
Thank you for that. Hello, everyone. Good afternoon. As you can see, this is on local connectedness on Bowditch boundaries. It's a joint work with Professor Chris Hruska from University of Wisconsin-Milwaukee. So we will start with one good example that we can keep in mind. So here is a picture to think about. We have a torus here with a punctured cusp torus. Its fundamental group is, of course, F2, and that's the free group in two generators. And I have drawn a little circle around here, which will mean something in a moment. So let's look at this in the context of the hyperbolic plane. So this is the Poincare disk model of the hyperbolic plane. And the circle around the disk, we think of it as the boundary, whatever that means. We can think of the F2, the free group into generators, acting on the hyperbolic plane in such a way that the quotient of the action is the cusp torus that we saw a moment ago. And this is a very nice way of thinking about this. The two generators of the cusp torus, of the free group, A and B, suppose. You can think of A as the hyperbolic isometry that takes the left to the right, and B as the hyperbolic isometry that takes the bottom to the top. And one thing we noticed in this picture, at least intuitively we understand, is that this fundamental domain, which is grayed out here, it's like this square that goes off to infinity in some sense, is not compact. And another thing that we notice is that the commutator of these two generators, A and B, these two isometries, the commutator fixes a point in the boundary down here. So the image is from a particular paper from Murphy page, so I should indicate that. The features of this particular example will actually let us understand, at least intuitively, that one of the main objects of this particular talk. What we saw is a group acting by isometries on a hyperbolic metric space. The fundamental domain of this action, we saw that's not compact. And some of the subgroups of this group are fixing points in the boundary. We call them parabolic subgroups. And we guess that maybe some of the subgroups are doing something on the points on the boundary. Maybe all of the group is having some nice action on the boundary. So these are the things that we sort of see as features of this example, which brings us to the main object of study that we have, the relatively hyperbolic group pair. It's a pair whose first slot, the first element of the pair, is a group. In this case, F2 was the first element. First is the group that we are thinking about. And the second slot is filled up by a collection of subgroups of this particular group. Now, in this case, the collection has only one element, that is the subgroup generated by the commutator of the generators of this free group. So that's one thing that we are interested in, a relatively hyperbolic group pair. And the other thing that we are interested in is the boundary of this particular plane on which, space on which the group is acting in this plan, which we call the Bowditch boundary in this case. So with this example as a backdrop, let's come to the problem that we are studying in this paper. So the main object of interest is the connected Bowditch boundary of a relatively hyperbolic group pair. It's the connected Bowditch boundary is the compact Hausdorff metrizable topological space. So that's the kind of animal we are dealing with. And the main theorem of our paper is that if this particular topological space if the Bowditch boundary is connected, then it is also locally connected. Let me talk a little bit about the motivation and history of this problem so that we see it in some context. Relatively hyperbolic groups are widely studied in geometry group theory. And it's a generalization of hyperbolic groups introduced by Gromov in his highly influential work from 1987. In this talk, I will not give a definition of a relatively hyperbolic group pair. I will just indicate that we talked about some special collection of subgroups of the group G, which is occupying the second slot. Examples to keep in mind are the fundamental groups of complete finite volume hyperbolic manifolds. Also, the relatively hyperbolic group pairs act by isometries on some hyperbolic metric space, but the action is not necessarily co-compact. That is, the fundamental domain is may not be compact. So we saw that in our example as well. And the other object is the Bowditch boundary. It's a topological space, as we mentioned earlier. It's uniquely defined up to homeomorphism for a given relatively hyperbolic group pair. The parabolic subgroups of the relatively hyperbolic group pair, that is the member of that dark P, those special set of subgroups, they fix points in this particular space M. There's a special action of the group pair on M, known as geometrically finite convergence action, which I'm not going to define today. Now, the reason we are studying these two things together, the relatively hyperbolic group pair and the Bowditch boundary M, is because it's actually bears from a general strategy in geometry group theory. It's like this, that start with a group that you want to study, and then construct a space on which the group acts in an interesting manner. In this case, Bowditch boundary is the space. And the topological data of the boundary may reveal some interesting information about the underlying group. So moral is that it is useful to study the topological properties of the Bowditch boundary, which brings us to the main question, that is the connected, if the boundary is connected, is it locally connected? Actually, Bowditch studied this problem around 1999. There was a series of papers in which he tried to answer this question. And he found, yes, indeed, it is locally connected, provided you have some restrictions on the group and the members of P, the collection of parabolic subgroups. And the restrictions were like G, the main group, has to be finitely presented, and the members of P, that is the special collection of subgroups, the parabolic subgroups, they must be tame. Tame in this sense means that they must be finitely presented, they must be one or two ended, and they should not contain infinite torsion subgroups. So under these restrictions, it was proved that indeed the Bowditch boundary is locally connected if it is connected. Now, in 2022, the paper that we have, it removes all of these restrictions on the parabolic subgroups. And moreover, it also removes any countability assumption on the main group. Of course, this is of purely pedantic interest, I guess, because all the good examples of relatively hyperbolic groups are, they do not need infinite generation. So anyway, but we also remove the extra restrictions on the parabolic subgroups. That is, it is now true for all relatively hyperbolic group pairs. Now, this has been a quite an useful. We think it would be a useful result so far. There is some evidence from the literature. For example, Hallmark and Hruska used it in understanding elementary splittings of one-ended relatively hyperbolic groups. Mihalik and Svensson used it to understand the semi-stability at infinity. Hruska and Walls used it to understand relatively hyperbolic group pairs with planar boundary. Hallmarks, there's a paper by Hallmark in 2019, which tried to classify, which classified certain special types of relatively hyperbolic group pairs, boundaries of them. And a very easy corollary of that using this theorem makes the classification more general. There are certain directions I am thinking on using this theorem, using this result. It's related to the quasi-isometric embedding of hyperbolic planes in relatively hyperbolic groups. It's also a very old problem. If someone is interested, they can look into the works of Bong, Kleiner, Mackay, or Sisto. Local connectedness could be an important component of that project. Now that we have set it up, and the sort of the motivation or the main idea, main theorem, let me talk a little bit about some of the things that we did in the proof, some of the things that can be useful in maybe in some other project. So recall that the relatively hyperbolic group pair has an action on the boundary, the Bowditch boundary M, and I gave a name. I used a long name for that action, geometrically finite convergence action. But as I said, I wouldn't define it. One of the interesting things that we could do is translate this convergence action, which is on the boundary and on the topological space M, into a non-nesting action on an object called pre-tree. Now, pre-trees were studied by Bowditch and other people as well. And you can, if you want, you can go into some of those classical works to understand them. They are tree-like structures. Literally, there was a book, I think, with that name, tree-like structures. But if intuitively, that's what they are. What we did is we started with the boundary M, the Bowditch boundary M, and we converted it, or such, I shouldn't use convert, we extracted a pre-tree K using the cut point data in that boundary. Now, of course, to do that, we have to assume that there is a cut point, which we did, which is part of the proof strategy. And the convergence action on M induces an interesting automorphism on K. So there are certain dynamical properties of the automorphisms of this pre-tree object, which were very useful in the main theorem. One of the very simple but beautiful things that were part of this dynamical properties, that these automorphisms are non-nesting in the interior of the pre-tree. Interior means you just throw away the terminal points, and whatever is left is interior. And you non-nesting essentially means that no interval is properly mapped inside itself. So there is a concept of interval in a pre-tree. You can define it, and if you can sort of intuitively understand what it is, then non-nesting means that that interval is not properly mapped inside itself. So we use the non-nesting property of the pre-trees quite extensively. Here is a picture taken from this particular paper by Papasoglu and Svensson. It's from Continua to R3. It's an example of a pre-tree construction. So for each of the cut points, you draw a dot. So these black dots are for the cut points. And if 2 points cannot be separated by a cut point, then those are equivalent points. That induces an equivalence relation on this on X. So this particular big ball reduces to 1 point. This circle, look, that these 2 points, I don't know if you can see my cursor, these 2 points are not separated by a cut point, so they are equivalent. In fact, all the points on the circle are equivalent except for these 2 cut points. So they reduce to a green dot and so on. So this P is the cut point pre-tree. And then, of course, you can convert it into a cut point tree by connecting the dots. Now, of course, that has a precise meaning as well. So one these definitions can be found in construction, also can be found in the paper of Swenson, that you start with a continuum. A cut point is, of course, if you remove that, M is no longer connected. And then you define an equivalence relation on M. Each cut point is, of course, equivalent to itself. And if A and B are not cut points, they are equivalent if they are not separated by any other cut. So the cut point pre-tree is the set of equivalence classes under this equivalence relation. And if you connect the dots, you find the cut point tree. So we used it quite a lot. And as I said earlier, that the convergence action induces a certain type of action on this pre-tree K. So the setup is like this, that suppose you have a group pair that has a minimal convergence group action on a continuum M, and capital C is a G invariant collection of cut points in M. So maybe you can take, what we did is we took the translates of a particular type of cut point. And we formed the cut point pre-tree K out of that collection of cut points. And K prime, I will denote it as the interior of K, that is removing the terminal points of that particular pre-tree. And with this particular setup, the induced pre-tree automorphisms have these properties, that G will not fix any point of the cut point pre-tree K, and the action of K is without inversion. So you can, if you have two adjacent points, the pre-tree automorphisms will not flip them. Action on the interior is non-nesting. The interval stabilizers of this interior are elementary as viewed as convergence group, a subgroup of the convergence group. And if each of the peripheral subgroups of the relatively hyperbolic group pair are finitely generated, then each of those peripheral subgroups will fix points in the interior. So that is one kind of object that we widely used in our paper. The other part, I also wanted to give a little sort of overview how the proof flowed, so that we can communicate what tools we actually used. There are several new discoveries since the work of Bowditch, which helped us to put this entire thing together. So one way to see the Bowditch boundary is an inverse limit of tree of spaces. What you do is you glue the boundaries of the vertex groups of an underlying tree. Right, it's actually a JSJ tree, but anyway, you glue the boundaries of the vertex group of that particular tree, and that inverse limit of that sort of tree of compacta gives you the Bowditch boundary of the entire relatively hyperbolic group pair GP. So what we show is that each of the pieces, that is the boundary of the vertex groups, are locally connected. And then we piece it together using a theorem by Capel to show that the entire thing is locally connected. So that's how the thing flows. And when I say pieces, what I mean is that we start with a JSJ tree of cylinders, which are over parabolic subgroups relative to P. Okay, I don't think I have time to go into that. But anyway, so yeah, so the main thing is this, that we break down the entire Bowditch boundary in these pieces and show that each of the pieces are locally connected. Now, how do we show that? How do we show each of the pieces are locally connected? We actually obtain a certain kind of using the non-nesting action, we obtain a splitting of certain kind of vertex groups of those pieces. So we see the splittings of those pieces again. And that actually leads us to a contradiction, that certain unsplittable pieces become splittable using the relative Lipps machine that was from the work of Gödel and Leavitt. So I'll stop out here. I think I'm out of time. Thank you for watching. I'll just waiting for questions. Thank you.
Okay, let's thank Ashani. We could use our thumbs up emojis or clapping emojis or just clap. Does anybody have any questions?
Question.
Yeah, feel free to just jump in and ask.
Okay, good morning. I have a question. You didn't define the Bowditch boundary, yeah, but is there a way you can like see it in, I don't know, some boundary of the Cayley graph, or like what is the intuition behind this Bowditch boundary? What should I expect this thing to look like? I don't know if the question makes sense.
No, of course. So one way to see it is like this, that you start with the Cayley graph. If you want to do that, that's a great place to start. And then you take the cosets of the parabolic subgroups. Remember, I specified a collection of subgroups, which was script P, right? So you take the left cosets of those parabolic subgroups, and then to them you attach a horoball. So I'll have to define a horoball again. But you attach something to those cosets, and the resulting space, the boundary of the Gromov boundary of the resulting space, you can give you an intuition about what the Bowditch boundary should be. I don't know if that answers your question, but it is, you have to do something to the Cayley graph to get the boundary.
Yeah, okay, it makes sense in the example, so I get it. Thanks.
Sure, thank you for the question. Yes.
I would like to ask a question about this tree of spaces. Could you please elaborate a little bit on that? What it is, or?
Yeah, I mean, intuitively speaking, again, there will be an underlying tree, a bipartite tree, and let's call the two colored vertices as red and blue, let's say. Now the red ones will be the fat ones. Fat ones means which will have, it will be like a subcontinua of M. And the blue ones will be singleton points, suppose. And what you do is, there is the data of the JSJ tree gives you a recipe to stick together the subcontinua in the tree-like pattern, and the sticking happens along the parabolic fixed points. So, and then you take inverse limit of that. So that's why we call it tree of inverse limit of tree of spaces. The spaces are the subcontinuous, stuck along points. Schwartowski, I'm sorry, I do apologize if my pronunciation is bad, studied these objects widely. And then we also used the same idea here, similar idea here. Yes.
Thanks a lot.
Sure. Thank you for the question.
Any other questions?